Okay, so we are all set for today's lecture. Okay, so I think before lecture, I think we had okay um, quiz exam two. Okay, quiz two exam. How was it? Okay, is it okay? Is it fine or not?
It was good, sir.
Okay, okay. Any other thing? Any feedback? Anything? I could see some messages. Okay, in the group, in the WhatsApp group, I could see some messages, some feedback. Okay. So I haven't started evaluating it. I'll do it. Okay, this weekend. So too much noise. Are you hearing this noise?
Yeah.
Yes, sir, it is coming that noise.
We don't have much control here. But, okay. So in my previous lecture, okay, okay, we had two lectures, okay, on crystallographic texture. So crystallographic texture is one of the important microstructural aspects, okay, which plays significant role on mechanical properties of a material. Okay, so because especially when you talk about okay polycrystalline materials, we do have grains of different orientations. So during some process, we may see evaluation of some crystallographic texture. Preferred orientation may evolve okay due to some processes. So the processes can be solidification, plastic deformation, recrystallization, okay, and we also see a thin film deposition. So many processes can induce textural change. Okay, by crystallographic texture is going to change in polycrystalline materials. So the texture can be represented okay by different means. Okay, three important means actually: by means of pole figure, by means of inverse pole figure, and also by using orientation distribution function. Okay, so pole figure look like this. It will uses specimen coordinates RD, TD, and D, rolling direction, transverse direction, normal direction. Okay, in case of inverse pole figures, we use crystallographic okay crystal orientations. Okay, crystal orientations will be used to represent the texture. In case of okay ODFs, okay, we use okay Euler space representation. By using Euler space, we can actually identify the type of texture what is being developed okay in the material. So just 1 minute. Just calm down. Okay, let's see. Let's hope that okay you won't get noise again. So ODF orientation distribution function is very much useful way of representing texture, which can be used for quantifying different types of texture components, whatever present in a material. Various texture components can be quantified. Okay. So the quantification is basically involves, okay, by using Euler's angles, positions, and their fractions can be identified. One can actually know volume fraction of various texture components. So various texture components in, okay, cubic materials, typically what we see, okay. Am I audible still? Am I audible?
Yes, sir.
Yes, sir.
Okay. Yeah, I think please bear this noise, okay. So a lot of construction work going on today, I don't know. Okay. Let's see, okay. So in various texture components we do see like fiber textures, okay. We also see like a copper texture, brass texture, S type texture, gauze texture, delomere, cube texture components, okay. These are popular texture components what we see, okay, during deformation and during recrystallization, okay. Because of deformation, because of recrystallization, we may see some texture components are going to evolve depending on material to material and amount of strain, how much you are giving, okay. So various factors can dictate the texture evolution in a material, okay. Usually during deformation what we talk about: temperature, strain rate, and strain, okay, and initial microstructure, initial texture what is there, that also can dictate what type of texture is going to evolve in a material during deformation and during recrystallization or any during annealing treatments. So we do see some texture changes are going to happen. So cube texture, okay, quite commonly observed, okay, during recrystallization. When you do recrystallization after deformation, okay, if you do recrystallization, we do see cube texture is going to develop. During deformations, depending on stacking fault energy, okay, the stacking fault energy is low, we do see brass type of component is going to be dominant, okay, as compared to copper component. Okay, the S component basically is a comes, okay, in between, okay, brass and copper. So gauze texture is going to be evolved, okay, in a coarse grain material, certain materials, okay, like iron silicon alloys. We do talk about gauze texture, which has a significant role in magnetic properties. So gauze component is actually important in certain materials. This also evolves, okay, most of the times during, okay, some amount can be evolved during deformation, some can evolve during recrystallization also. So in case of BCC, okay, IF steel, we talk about interstitial free steels, we do see, okay, a fiber texture, okay, is going to be dominant. The fiber texture what we see, okay, it's basically 111, okay, orientation parallel to normal direction. This is called gamma fiber. This is called gamma fiber. This gamma fiber can induce, okay, very good formability in the interstitial free steels, which are used for automotive car body applications. Okay. So then I think, so during deformation, how the text is going to evolve because of a shear deformation. Okay, because of shear and rotation together combination can lead to, okay, formation of a texture. So texture is going to evolve. Okay, basically the presence of rotation which can happen due to rigid motion of a body. So that can lead to texture evolution in, okay, materials during deformation. Okay, so I said, like, we already discussed copper type of texture. Okay, brass type of textures are going to evolve depending on stacking fault energy of material. Okay, so typical, okay, one can see fold figure change. Okay, by changing the stacking fault energy, we may see change in, okay, copper texture to brass texture in the material during same amount of deformation. Okay, then we also discussed, okay, when you draw wires, okay, okay, the wire textures, typically we use fiber textures. We usually talk in terms of a fiber textures. Okay, so the fiber textures what is going to evolve, okay, during wire drawing is also going to depend on stacking fault energy of a material. Okay, so we may see, okay, if you take aluminum, which is high stacking fault energy material, and if you take silver, okay, is low stacking fault energy as compared to aluminum. So the texture evolution, okay, in the, okay, as a function of stacking fault energy, if you see here, we are going to have a more 111 texture. Okay, 111 fiber texture will be more in aluminum, whereas in silver we are going to see dominant texture is a 100 texture. Afterwards, again, we do see there is a change in texture component. Okay, the ratio is again going to change. Your 100 texture component is going to come down. Again, okay, 111 texture is going to evolve. So this, okay, people have addressed in terms of, okay, the twinning. Okay, when you talk about very low stacking fault energy, so the twinning can induce again, okay, change in the texture. Okay, in a very low stacking fault energy materials. Okay, I think I stopped at this moment. I think lost in my previous lecture. If there are any doubts, okay, that's basically end to that. Okay, crystallographic texture. If there are any doubts, please let me know. Are there any doubts about the crystallographic texture? Okay, if there are no doubts, okay, so I will move on to new topic. Okay, so the new topic is related to cyclic plastic deformation, which is nothing but actually what we are talking about, a fatigue kind of, okay, deformation of a materials. So when you talk about mechanical testing, okay, when you test the material mechanically, okay, so there are different types of, okay, types of, okay, testing categories. Okay, it can be a static testing, quasi static, dynamic, or cyclic. That means the way you apply load to the material. Okay, people may say static testing, okay, or quasi static, dynamic, okay, cyclic testing. Okay, so can anybody say some examples for static testing? Static, that means actually very slow rate of, okay, deformation. The
Hardness
deformation what?
testing.
Which one? Say it again.
Hardness
Yes, sir.
testing, sir. Hardness.
No, hardness is not very slow. Okay, no, hardness is not very slow. Okay, it is a, okay, quasi static condition we do. Okay, tensile testing, axial testing also quasi static testing.
So creep testing.
Creep testing, okay, creep testing, okay, stress relaxation, creep testing, okay, command and cloud static, okay, very slow rate of deformation. The rate of deformation is very slow. So quasi static means, okay, the rate of deformation slightly higher, slightly higher. Okay, here we are talking about static means the rate of strain rate, okay, typically less than 10 power minus 5 second, 10 power minus 5 per second, kind of less than. Okay, so such a low strain rate we call static, okay, strain rates testing. When you say quasi-static, when you talk about quasi-static, okay, the strain rate typically 10 power minus 5 to, okay, 1 per second, typical, okay, 10 per second, up to 10 per second, we call quasi-static strain rate. Okay, so the example is basically axial testing, okay, tensile compression testing, for hardness testing, all come under category of quasi-static testing. So under dynamic, when you say dynamic, okay, the rate of deformation is very high. The strain rate is very high, like a 10 power 3 per second, 10 power 10, okay, 10 power 8 up to, okay. Typically high strain rate tests come under category of dynamic testing. Cyclic testing also come under some kind of dynamic testing, okay. But here the stress or strain is going to be cycled, going to be cycled. Okay, that's called cyclic testing. Okay, so these are a kind of examples. Okay, we talking about, okay, high strain rates, basically split Hopkinson Kolsky bars come under category of dynamic, okay, strain rate tests. Cyclic tests, fatigue testing, and damping come under category of cyclic tests. So what we are going to talk about, cyclic testing, basically fatigue, okay, deformation, plastic deformation of a material under cyclic loading conditions. If I look at here, some components which fail due to cyclic loading conditions, due to cyclic loading conditions. Here, if you see here, an automotive, okay, some, okay, vehicle has been shown here. Okay, some of the components will subject to cyclic, okay, stress conditions, cyclic stress or cyclic strain conditions, can fail, okay, with during, okay, working conditions itself, it can fail miserably. Okay, one such failure has been shown here. Okay, most of the times, okay, there is a, so if you look at here, there is an axle which basically drives the, okay, vehicle. So the rear axle, okay, usually fails, okay, because usually subjected to okay, cyclic loading conditions, it will fail. Okay, so the failure, okay, most of what we see, the failure of the rear axle has been attributed to metal fatigue, fatigue behavior. Okay, the fatigue deformation which undergo the axle undergoes, that can lead to fail. Okay, that can lead to premature failure of the component. This is one kind of, okay. So many of the automotive sector components, okay, like, okay, which undergo cyclic deformation, can fail due to fatigue. Okay, we are talking about metal fatigue. Okay, and the other components what I'm talking about here. Okay, what is this actually? Any idea
Connecting
what is this
rod.
huh?
Connecting rod.
Connecting rod, crank arm. Okay, so, okay, crank arm. Okay, what is this? Any idea?
Crankshaft.
Crankshaft. Yes, you are right. Okay. So we do see, okay, failures, whatever we see, okay, like that, for example, the material failing here, okay, it's failing, crankshaft is failing, crank spider arm is failing, okay, gear teeth also get failed, okay. We do see even aerospace components, okay, will also fail under cyclic loading conditions. So these things are attributed to, okay, fatigue failure of a components. So the fatigue failure, okay, is not, okay, new, okay, it has been there, okay, people have, okay, attributed many failures, many, okay, 80 to 90% of failure, okay, engineer components failure are attributed to, okay, fatigue failure. Okay, if you look at here, there is a history, okay, there is a the history from 1842 onwards, the failures, okay, of some of the components, some of the, okay, important failures, whatever you see, have been attributed to, okay, fatigue failure of a material. So the first fatigue failure was observed, okay, was reported, basically was reported in the year 1842. Okay, the train accident, okay, this train accident where the rail axle failure, okay, was found to be, okay, due to, okay, cyclic loading conditions. The failure basically due to cyclic loading conditions. So since then, people have, okay, studied about the fatigue deformation behavior of a material. So there have been, okay, some important, okay, stages, main events happen over a year. Okay, this is a table basically nicely gives summarizes some important events related to fatigue failure of a material here. Okay, so if you look at here, okay, the first scientific publication came from by Wöhler, who is a scientist, who is a, okay, a scientist who has actually reported this failure, whatever, okay, train failures happened during those days was attributed to cyclic loading, okay, conditions, basically simply called fatigue failure of a material. Okay, so he studied, okay, various components, okay, and subjected to bending torsion test and investigated what is the effect of stress on the failure of a material. Okay, afterwards there are so many, okay, new concepts have come, okay, and new, okay, studies have been established. So during that time you also see, okay, an important, like, aerospace, okay, failure what you have seen, okay, comet aircraft, okay, aircraft accidents, two aircrafts within a short duration, okay, within a short duration, two aircrafts failed miserably, okay, while it is in operation. Okay, so that led to, okay, pumping in lot of money to understand fatigue failure of materials. Okay, up to 1954 the studies are there, but not much, okay, devoted, okay, in terms of research wise, very limited research was there. But from 1954 onwards, okay, there was a huge, okay, amount of, okay, research has gone into understand fatigue failure of materials because of, okay, failures what we are seeing, okay, a lot of human, okay, deaths are involved in this failure. So that's why actually people have spent a lot of time and money to understand fatigue failure of materials. Okay, so I'll show you two, okay, videos which basically shows, okay, the failure of some of these, okay, 1954 aircraft, okay, how it failed, okay, and also one, I think, minor accident happened, it's basically 1988 Aloha. So these two videos are shown here for your better understanding. So the failure, for example, comet failure was actually attributed to fatigue failure of a material. Okay. Sorry. This animated video which was taken later. Okay, Okay, so this video basically shows, okay, which is basically presented in the National Geographic Channel, okay, how this flight, okay, BOAC flight 781 crash. This is called simply called Comet, okay, Comet aircrafts. Two aircrafts, okay, 1954-56, okay, within short duration time, two aircrafts failed miserably. It's considered as a disaster for aircraft industry. Okay, that was the time 1954 was the first disaster related to, okay, aerospace industry. So this failure was attributed to simply to the fatigue failure of a material. Can anybody say what did you understand from this video? How this, okay, failure happened? Can anybody just? Okay. I would like to know what is your observation from this animated video. Okay.
Sir, it is started from a notch, so it began to
Okay,
expand.
but it was attributed to fatigue failure. Okay. Why it is called fatigue failure? Why was it attributed to fatigue failure?
I don't
Sir,
know.
the rivets failed because of the continuous vibrations.
Where is vibration here?
Mm, Sir,
Rivets
because
not.
of
Okay, basically the failure happened in the fuselage. Okay, the skin. Okay, the skin aircraft skin. Okay, has undergone fatigue failure. That's what people okay reported. What is vibration here? I'm not getting. Vibration means what? Any other guess?
Sir, it may be because of the because of the number of cycles that that joint has gone through. So it may be
What
used
what
for
what is cycles here? Actually, you're talking about what
uh,
cycles?
just the time under duration. So that particular flight must have gone through many hours of flight before also, and after some
Where
time there
we
was the
said
crash.
fatigue failure is a cyclic deformation. Okay, change in stress or strain. Okay, where is the loading here?
Sir, it is due to the friction of the air
No,
on the skin.
no, that's not that thing.
It is due to the pressure difference from above and below.
Yes, you are basically this is usually when you do okay take off okay during taxiing take off okay while okay, going we do see pressurization and depressurization. Okay, all aircrafts will okay undergo pressurization depressurization. Okay, so depending on okay so that is where okay the pressure what we are basically we are subjecting the aircraft skin to pressurization depressurization, that where we are giving a cyclic loading condition. Okay, any aircraft okay while it's take off okay then while it's taxiing okay we do see so the pressurization depressurization cycles. So there we have pressure, that's a stress. Okay, so initial the crack okay whatever has formed because of riveting. Okay, when you put a rivets okay around the rivets okay the aluminum alloy has undergone some crack. So already cracks have been initiated by riveting operation manufacturing itself. So during okay cyclic pressurization depressurization the crack has been propagated. Okay, it's actually not old okay it's new aircrafts okay failed. It's not actually not subject just okay just pressurization depressurization led to the fine whatever okay minute cracks which have been formed due to riveting, those have undergone propagation due to pressurization cycles. So that led to failure of the Comet aircrafts. Okay, is it clear? The cyclic basically here pressure depressurization. Okay, so the another okay I think it's a accident only, not much okay I think fatality not much fatality error is not there, where I think two or three people I think died, but it's like okay it looks very funny kind of accident which has happened is also due to same okay fatigue failure.
April 28, 1988, when a 737 famously lost part of its fuselage in midair. As the 737 climbs through 24,000 feet, the cabin pressurizes and the skin of the plane expands just as it's supposed to. But something else expands too. Those cracks in the 737's decompression. Its force is so powerful, a flight attendant is sucked out of the plane.
That whole
An 18-foot section of the plane is gone. Passengers sitting nearby can see the sky above and the ocean below. All that's holding the 737 together, and just barely, are the.
After 13 extraordinary minutes in the air, it makes an emergency landing on the island of Maui. Investigators need to discover what caused this spectacular incident.
Okay, so this Aloha incident happened in 1988. Okay, this also has been attributed to fatigue failure that happened, pressurization, depressurization led to crack propagation in the skin. Okay, so the afterwards, I think, okay, 1996, okay, Pensacola accident also happened. Okay, where it's okay, some part of the engine has fallen. Okay, so the fuselage skin, which basically connecting, is got disconnected. So that led to some I think immediate I think landing happened. So that saved people life. So this kind of the accidents which happened and the failures whatever happened in aerospace components, that led to spend okay time to understand how the fatigue failure is taking place in a material. Okay, so the fatigue phenomena, now what is a fatigue now? Okay, so how do you define fatigue? We are talking about it's fatigue. Okay, it's a fit we all, everybody gets fatigued. Okay, that's called physical fatigue, and metals also get fatigued. Okay, so the word fatigue is basically come from a Latin word fatigere, which is nothing but a to tired. Okay, get tired. Okay, so the definition of a fatigue basically should involve cyclic stress or cyclic strain. That means repeating loading, repeating stress or repeating strain should happen. That can lead to failure of a component. Okay, so there should be a cracking or failure should happen due to repeated loading or repeated straining. So that can that failure is called fatigue failure. The phenomenon is simply called fatigue phenomenon. Okay, so this is how actually the definition of actual the textbook definition metal fatigue is basically applies to changes in properties of a metal due to the repeated application of stresses or strains. Okay, it should lead to cracking or failure of the material. So this is actual textbook information, the definition of a metal fatigue. In a simple sense, metal fatigue basically which can cause premature failure or damage of a component subjected to repeated loading. So this is called actually in a simple manner calling what is metal fatigue. So it basically it should involve cyclic activity. Okay, that means there should be a change in stress magnitude or strain magnitude that can lead to premature failure of a material. So the actual fatigue phenomena is basically involves significant amount of plastic deformation under cyclic loading conditions, under cyclic strain conditions, under cyclic stress conditions. We do see the material can undergo plastic deformation. So this is that deformation is basically called cyclic plastic deformation. Okay, so the fatigue process involves two stages. Okay, two distinct two actually important stages will be involved. One, crack initiation. Okay, formation of a crack is going to get initiated, and this crack is going to propagate during further deformation. That means crack initiation, crack propagation are two important stages. So the stage one, typically crack initiation and a small amount of propagation in micron level. Okay, very small micron size crack is going to propagate. Okay, that's called this whole stage is called crack propagation stage or crack initiation stage. And stage two is basically simply crack propagation stage. Okay, so these two stages basically crack initiation. Okay, the amount of time required to propagate the initial whatever crack has been initiated, the amount of time required for crack initiation plus for having a micro crack formation, micro crack formation. This is called crack initiation life. The amount of time required for stage one is called crack initiation life, and the amount of time required for crack propagation, that is called crack propagation life. Okay, so it basically same thing. Nucleation, early growth of a small crack in a component is called crack initiation, and the total propagation, final propagation lead to failure of the component, that is called crack propagation life. Okay, so these two important stages will happen are going to take place in a fatigue process of a material, fatigue phenomenon of a material. So it's very much important. Okay, one has to know how many number of cycles are required, what is the time period, okay, we need to have, okay, for crack initiation, and how much time is required for the crack propagation. So together will give you total number of cycles for the material to fail you, okay, the material component to fail. Okay, so in order to understand fatigue, okay, behavior of a material, fatigue behavior of a material, so the analysis people do by three different means. Okay, one, okay, stress life approach, one is called stress life approach, other one is called strain life approach, and the third one is a fracture mechanics approach. By using three different types of approaches, people try to understand, okay, fatigue behavior of a particular selected material or a component, whatever you're talking about. So people try to see, establish, okay, by changing the stress, okay, and understand how many number of cycles are required for the material to crack to initiate, a crack to propagate. Similarly, when I say strain life approach, we just simply change the strain, fix the stress. Okay, when you talk about it, now I'm just only vary the strain and see how many number of cycles are required, okay, for the material to crack, okay, to fail. In case of fracture mechanics approach, linear elastic fracture mechanics approach is used to understand, okay, crack propagation under cyclic loading conditions. Okay, so the stress life approach and strain life approach basically involves, usually we take a specimen, dog bone kind of specimen on a lab scale. Okay, you can also take a component subject to stress life approach, strain life approach, but typically if you want to understand a new material, how it is going to fail you, how it is going to fail under cyclic loading conditions, we usually, okay, use either stress life approach or a strain life approach. Okay, and also people also use, okay, fracture mechanics approach. In case of, okay, stress life and strain life approach, typically we take a tensile specimen, okay, having a dog bone shape of kind of thing. So this, okay, specimen will be subjected to either, okay, varying the stress or strain, okay, by changing the strain or by changing the stress. Okay, if you change the stress, okay, which is called stress life approach. If you change the strain, that is called strain life approach. That means we are defining the stress limits or strain limits, okay, by defining stress and strain limits, and subjecting the material to certain number of cycles, and we see whether crack has been initiated and how it has propagated. Okay, so one can establish how many number of cycles are required, total number of cycles required for the material to fail under given set of, okay, strain conditions or stress conditions. Okay, so this is called actually like a stress life, okay, stress life approach and strain life approach. In case of fracture mechanics approach, people usually take compact tension specimen, CT specimen, okay, like this, and it already has a crack, okay, already crack has been formed, and what we see how the crack is propagating, okay, the resistance to, okay, crack propagation is established under cyclic loading conditions and using a fracture mechanics approach. Okay, any doubts here? Are there any doubts? No? Okay. So the most popular one initially, okay, people used to use, okay, stress life approach. Okay, earlier studies are involved, okay, stress life approach. After, okay, I think around 1930 onwards, people have started also developing strain life approach. So this fracture mechanics approach come, okay, 1950s, around 1950s, fracture mechanics approach has come to understand resistance to crack toughness basically. Okay, indirectly toughness under cyclic loading conditions have been studied. So the stress life approach was developed by Wöhler. Okay, Wöhler.
Hello, sir.
Sir is not audible, correct?
Yes, yes, yeah. I just actually want to confirm. Okay.
Hello?
Hello.
Yes, sir. Now it was you are audible, sir.
Yeah, I think which slide I missed it. Okay, my lecture. Any idea? I'll share my lecture slide.
So you were on that slide, the three approaches, stress strain.
After three approaches, sir. Sir,
After three. Okay, okay, then it's fine because I don't suddenly it's lost. Um, Is it clear about the stress life approach and strain life approach and fracture mechanism approach? Basically, okay, we are talking about how to quantify fatigue, okay, phenomenon of a material. Okay, so the stress life approach, we usually we apply stress range. Okay, we maintain some minimum and maximum stress, minimum and maximum stress. Then okay, then cycle. Okay, subject the material under that okay minimum and maximum stress. That is called stress life approach. If I deform material, okay, between strain limits, I define the strains, okay, and monitor, okay, how many number of cycles are required for its failure. Okay, in case of okay fracture mechanism approach, we usually just monitor how the crack is propagating, okay, under cyclic loading conditions. Okay, so the life approach, the stress life approach was given by okay Wöhler. Okay, so he okay came up with some experimental setup to apply torsion and bending that can give idealized stress conditions. Idealized conditions, that means equal amount of okay stress, minimum and maximum, but opposite direction. Okay, tension and compression. Okay, sigma max and sigma minimum, the magnitudes are same, only thing it's opposite in sign. Okay, so that can okay, idealized stress condition. Okay, idealized stress condition, sigma minimum by sigma max is basically equal to -1, is equal to -1. That idealized stress condition, if you apply idealized stress condition, okay, we can actually okay once you define a stress amplitude basically sigma max minus sigma minimum by 2, that is basically stress amplitude. Okay, by giving a different stress amplitudes, we can monitor okay number of cycles the material required okay for its failure. Okay, so that is called fatigue life. Okay, what at a given stress amplitude, how many number of cycles the material has experienced before its failure. Okay. The total number of cycles, okay, the fatigue life is basically summation of number of cycles required for crack initiation plus number of cycles required for crack propagation. Okay, with the decreasing stress amplitude, okay, the number of cycles to failure usually increases. Usually increase at a given stress amplitude. This is the number of cycles. That's called fatigue life. So with the decreasing stress amplitude, typically the fatigue life is going to increase. Okay, but okay out of the total okay fatigue life, the crack initiation, the stress required, the number of cycles required for crack initiation is going to be more, okay, with decreasing okay stress amplitude given to the material. Okay, is it clear about the okay, this curve is typical called SN curve. Okay, the final curve what you get, okay, it's called simply called stress versus number of cycles curve. It's also called Wöhler curve. Any doubts here?
Sir, is this valid for all materials?
No, it's not valid. Okay, valid means actually typically okay, it's valid in terms of okay with decreasing stress amplitude, number of cycles required for fatigue failure is going to increase. That is valid. Okay,
Okay.
the shape of the curve may vary. Okay, depending on material to material, the shape of a curve. Okay, for example, in this case, we are seeing a after some amount of okay below some certain stress amplitude, we are seeing almost like a constant steady. Okay, number of cycles are increasing. Okay, there is not much okay, change. So this is called okay. So this can be seen only steel kind of ferrous materials one. We don't see this kind of behavior non-ferrous materials, where actually non-ferrous materials continuously decreases. Okay, because So when decreasing stress amplitude, continuously the number of cycles are going to increase. Okay.
So what is NI and NT?
It's the number of cycles required for crack initiation. Okay.
So with decrease in the stress amplitude, the NI is getting increased, but
Yes.
the difference between NI and NT is reducing.
Yes. Yes.
That means it will initiate lately but propagate very fast.
Very fast. Yes. At low stress amplitudes.
Okay.
You are right. Okay. So there is an important concept called fatigue limit. Okay. From the stress from SN curve, people establish fatigue limit. Okay. The fatigue limit is also called endurance limit. Okay. So the definition of endurance limit, usually in ferrous materials, because most of the studies were conducted in ferrous materials earlier. So now it's because of importance of other non-ferrous materials like aluminum alloys. Now people also developed fatigue studies on aluminum alloys. But earlier, when steel was subjected to fatigue studies, so people have seen kind of almost like a saturated things, the stress amplitude below this stress amplitude, even if you give an infinite number of cycles, the material is not going to fail. So this curve basically tells, this is the safe regime. Above that curve, it's the unsafe. The material is going to be unsafe. It's basically, this curve basically tells, the boundary for the safe and unsafe. Okay, so the material is going to be safe. Below this. If the material is going to fail, if I apply, this much stress amplitude, this much number of cycles, the material is going to be unsafe. That means it's going to fail. So here the fatigue limit basically tells, below this, even if you give infinite number of cycles, if you, for example, at this stress amplitude, the material is not going to fail even if you give infinite number of cycles. So the minimum stress, below which the material is not going to fail even if you give infinite number of cycles, that is called fatigue limit. Okay, it's very much important property that is usually deduced from SN curve. Okay, so in case of non-ferrous materials where we do not see this steady saturated kind of thing, so there we take typically certain number of cycles, 5 into 10 power 8, 5 into 10 power 8 cycles. What is the stress amplitude? Okay, that means actually if we apply stress below that stress amplitude, below the stress amplitude below that, the material is not going to fail. Okay, so in case of steels, it's very well established. You can see very easily. Okay, one can establish what is the stress amplitude below which the material is not going to fail even if you go infinite number of cycles. In case of non-ferrous materials, we usually take a fix the number fatigue life. We take 5 in 10 power 8. So 5 in 10 power 8 below that many number of, for that given 5 in 10 power 8 cycles, what is the stress amplitude? Okay, so that stress amplitude is considered as a fatigue limit for non-ferrous materials. Okay. So this is important property. Fatigue limit is important property that can be deduced from the SN curve. Is it clear? Any doubts here? Yeah.
Hello, sir. How can we distinguish between initiation period and propagation period?
So this is actually not possible initially. Okay, that is possible only after when fracture mechanics approach. From the fracture mechanics approach, we can know. But from the test, from a simple test, is difficult to monitor. Okay, so this was established only later. That's what I said. Okay, this thing, how many? This was established only after having an understanding about fracture mechanics approach. So people have tried to see how many number of cycles are required for crack initiation, and how many number of cycles are required for crack propagation. That was actually done using a fracture mechanics approach, not by this is a stress life or strain life approach.
Okay, sir.
One has to monitor. It's not easy. Okay, so fracture mechanics approach can tell you how many number of cycles are required for crack initiation, crack propagation.
Sir, as the stress amplitude is decreasing, like the initiation period is increasing, but that propagation period is decreasing. So why like it should be constant, right? Or why like with the decrease of stress amplitude propagation, like if we consider the fatigue limit, at that very small point, like what we see, the initiation period is high, and there is almost zero propagation period. So,
Yeah, crack will be initiated, but it will not propagate. Okay, so cracks can be initiated. Okay, that length of the crack, okay, will not be sufficient to propagate. It need actually minimum some crack length, okay, for crack to propagate further. Because what happens, okay, there is a curvature, okay, the tip curvature is going to get affected, okay. So we need more amount of time for the crack, okay, crack initiation. So once you get that particular curvature of the crack, okay, that can propagate very quickly.
So that means like when the stress amplitude is like decreasing at it, and it comes close to that fatigue limit where the line is being horizontal. So at that time, the crack initiates, and without propagating, the material fails.
No, actually, what? Okay, here actually, yeah, close
Yeah,
to
yeah,
here.
yeah.
That yes,
Yes,
okay,
yes,
yes,
yes.
okay, yeah. Usually, the material can fail very quickly without much time requirement at low stress amplitudes. The propagation, okay, very fast. Okay, once you have certain, the length is going to be significant length, it can propagate quickly
Okay, okay. That propagation period is with reference to the time.
with respect to time scale. Okay,
Okay,
yeah,
okay.
when you say fatigue life, usually number of cycles we are talking about the time scale. Okay,
Okay, okay. I got confused with that. Like, okay, 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 fine, got it.
the period. Okay, the period. Okay, initiation period and propagation period.
So, propagation period coming down, is it good or bad?
Is it no? Basically, initially first, okay, you have to control the cracking, okay, crack formation. That's
Okay.
more important. Okay, crack initiation is more important. Okay, if we extend the crack initiation, that's good. Once crack initiation happened, propagation can be controlled by different means. Okay, if there are nothing to stop the crack, then it can propagate very quickly. Both are important. Okay, I'm telling you nothing actually. Okay, both are important, but actually initial, if the crack is there on it, if crack is the important first.
Okay.
Crack is not there, then you don't see any failure.
Right. Sir, and anything we can know about the crack length, as you said, because you said that if the crack length is more only, then it will propagate. But if it is less, then it won't propagate. So through this graph, can
We
you get a
can't say
measure
anything.
of that?
We can't say anything. From this
Okay.
plot, nothing can be okay. We can know just okay. One can monitor okay what is the total number of cycles required for material to fail okay under given stress sample two. Okay, at each given stress sample, what is number of that's it. We cannot give. So these things were established later. The understanding has come okay later. Okay.
Okay, sir. Understood.
So this is about the stress, okay, SN basically stress life approach. In case of strain life approach, okay, there are what we do, we just vary the strain, okay, we just okay vary the strain, okay, and monitor how many number of cycles required for material to fail. Here, for example, here, okay, when I say here, so there is a strain has been fixed. The okay strain has been fixed here. So the delta epsilon, basically maximum strain minus minimum strain. Okay. That's basically strain range by 2. Strain range by 2, basically strain amplitude. Similar to stress amplitude, here also strain amplitude basically maximum strain minus minimum strain by 2. Basically, we are defining material between a strain limits. Okay, when you apply strain, okay, deformation, when there is a deformation in the material, the deformation can be having elastic deformation plus plastic deformation, depending on okay how much strain range you are giving, okay, or similar stress range what you are giving. So the material can undergo elastic deformation or plus plastic deformation, depending. Okay, sometimes we may not see plastic deformation. Mostly we see elastic deformation in a bulk. In a bulk manner, we may see overall material may be experience only elastic deformation without okay. When you go to lower strain amplitudes or lower stress amplitudes, the material might be seeing overall the whole material might be seeing only elastic deformation. When you go to higher strain amplitudes or high stress amplitudes, the material can experience elastic strain plus plastic strain. Okay, the material can undergo elastic deformation plus plastic deformation. Okay, so the strain life approach, okay, the advantage of strain life approach, we can actually apply okay this strain range even in a plastic regime also. Okay, that means we can apply okay very high okay plastic strain regime also. In case of stress life approach, most of the studies were actually involve only elastic deformation. Okay, so when there is elastic deformation only, okay, in a bulk manner, I'm talking in bulk manner, okay, but locally there may be a plastic deformation, but in overall bulk manner, we may see the stress ranges what we are giving, okay, involve only, okay, elastic deformation part. In case of, okay, strain life approach, we can give, okay, we can have a better control over, okay, giving a strain range which involves both plastic strain plus elastic strain. Okay, so one can establish, okay, a full SN curve. Okay, so you can establish strain RHS stress versus number of cycles to failure. One can establish a range of strain. Okay, number of cycles can be, okay, can be understood how the material is going to behave as a function of strain amplitude or stress amplitude. When I say strain amplitude, that means actually I'm controlling stroke. The stroke of, okay, when you apply, okay, deformation, we are applying controlling the stroke. In case of stress, we are controlling load control. Okay, strain control experiments are actually better to, okay, better to monitor and apply onto the material as compared to stress. Okay, so strain life approach is a very good approach which basically can be used to establish, okay, a wide range of number of cycles. Okay, that means actually we can change the strain or stress to very high amount. Okay, low elastic stress as well as plastic stress also can be given. So this, okay, approach, strain life approach, once we establish, okay, by changing the strain ranges, we will get a kind of this kind of curve. So people try to analyze, okay, we have to analyze this, okay, total SN curve, so into two parts. One actually coming from a, okay, one coming from a plastic deformation part, other one is coming from a elastic part. Okay, so if we take a tangent of this initial, this part, okay, and tangent of this part, okay, will give you, okay, two regimes. Okay, elastic plastic strain part and elastic strain part, and there is a intersection, there is a transit. Okay, there is a transit. Okay, it basically tells, okay, below this transit, okay, it is called low cycle fatigue. Low cycle fatigue. Above this transit, okay, this will transition, because you have a transition. So above this transition we call high cycle fatigue. So the fatigue what you are talking about will be two types, categorized into two types: low cycle fatigue and high cycle fatigue. So low cycle fatigue, that means low cycles. Okay, the amount of number of cycles required for failure is low. That means you are applying very high stress or high strain. That means the material is undergoing already, in a bulk manner, is already undergoing plastic deformation. If the number of cycles are more, okay, that is high cycle fatigue. Okay, where actually what does it mean? We are giving mostly, the material is undergoing mostly elastic deformation. Okay, so that is called actually high cycle fatigue. So this transition, okay, is very much, okay, people do establish the transition will be established for various materials. Accordingly, we call low cycle fatigue and high cycle fatigue behavior of a material. Any doubts here? Are there any doubts?
Sir, one thing, sir, in the SN curve, you told that in bulk it only involves elastic stress, but over here also to involve the plastic stress, you will have to give that particular amount of stress, right? So if you increase the stress and go towards the plastic region, even in the SN curve, you can obtain plastic or not.
Yes, yes, it's a plastic. It undergoes plastic deformation. But actually, I'm telling the control, okay, is easy. Okay, the control, the stroke control is very easy to give even plastic strains. You can deform material within the given strains. You can go beyond plastic deformation. Okay, it's beyond elastic deformation. You can go. The material can be subjected to both elastic plus plastic deformation under strain control experiments very easily.
Okay, but why that control is not obtained in the SN curve? In
So
the
SN curve usually established, okay, using a, okay, usually established by using a stroke, using a load control. Okay, the loads, okay, controlling at high loads is not easy. At low loads, very easy to control.
Okay.
Okay, nowadays we have come up. Okay, we have a electromechanical systems. There we can control, okay, loads also. But actually earlier hydraulic, okay, these all are actually hydraulic based machines. Okay, if it, for example, even if you take in UTM, universal testing machine, okay, where, okay, we can use hydraulic test where it can give you cyclic loading conditions. So the means of applying load control is difficult, okay, and at high stresses. It's very easy at low stresses. The material, once a movement under material sees plastic deformation, it's not, it suddenly fails. Okay, it's not easy to monitor how many number of cycles are required under load control. Under stroke control, we can monitor how many number of cycles the material has experienced before its failure at high stresses.
Okay, sir. Sir, and can you explain the this two phases again, just before that, uh, before the equilibrium number of cycles to the left and to the right? That
These are called transition. Okay,
okay.
so basically, if you have a full, okay, you established, okay, from one cycle, okay, one cycle to, okay, some, hello, am I audible?
Yes, sir, you're audible.
Yes, yes. Okay. So from once you go from one cycle to, okay, establish up to, okay, 10 power 9 cycles, up to 10 power 9 cycles. So we'll get a complete, okay, stress strain curve. Okay. So from one cycle to 10 power 9 cycles, okay, we'll get two slopes. Okay. Okay, if you take two tangent of, okay, initial portion here, top portion, and, okay, bottom portion, if you take, so we do get, okay, there is intersection. So that intersection is called transition cycles. Okay, below the transition cycle is called low cycle fatigue. Above this is called high cycle fatigue. So the high cycle means actually the material is undergoing mostly elastic deformation. Okay, in case of low cycle, the material is undergoing mostly plastic deformation. That means the plastic deformation component is more in case of low cycle fatigue. In case of high cycle fatigue, it is called, okay, elastic deformation part is more as compared to plastic deformation. Okay, so this transition one has to establish, okay, to study the material, because depending on application, some applications the material may undergo only low cycle fatigue. Okay, in some application we may see high cycle fatigue. So one has to know what is the, okay, limit, okay, the stress amplitude limit, the strain amplitude limit we have to give in order to be high cycle fatigue. Okay, or if it has to be a low cycle fatigue, what is the stress amplitude or strain amplitude we have to subject the material. So for each material you have to establish, okay, this, okay, transition number of cycles which required the material to, okay, undergo low cycle to high cycle fatigue transition. Okay, so when I say here, okay, this part, okay, that means you are giving very high stresses or high strains. That means the material is already experiencing significant amount of plastic strain. Okay, so that part, okay, that tangent is different than the elastic deformation part. Okay, what you're seeing, this tangent is different. So this slope, okay, the elastic deformation slope is usually given B, and this slope is basically given C. Okay, so here most of the stress life approach, okay, the what we discussed earlier, what involved in this regime. Most of studies are involved in this one. If you use strain life approach, I can also establish this low number of cycles. Okay, 1 2, that typically comes around, okay, 10 power 3 to 10 power 4 cycles. The transition, okay, varies, okay, depending on material. It can be anywhere between 10 power 3 to 10 power, okay, 4 number of cycles, the transition cycles. Okay, below, okay, 1000 or below 10,000 cycles, typically low cycle fatigue. About the 10,000 cycles we call high cycle fatigue. Okay, so this, okay, analysis of this, okay, this part what you are talking about, it can be mathematically expressed. Okay, can be expressed like this. Okay, the strain amplitude, okay, is basically can be taken one actually elastic deformation part plus plastic deformation part. Okay, so this thing is called Baskin equation. Okay, this basically involves, okay, elastic deformation analysis, the curve which is coming, okay, that basically taken care by the Baskin analysis, and the plastic deformation part is taken care by Coffin-Manson. Okay, Coffin-Manson equation basically takes care of the plastic deformation part. So together basically gives you your total strain amplitude is basically can be expressed like this. So by using this one, okay, these are material properties. This coefficient sigma f prime, okay, is called like a stress coefficient, fatigue stress coefficient. B is a Baskin exponent. Nf number of cycles to failure. Okay, this epsilon f prime. Okay, this strain amplitude, okay, strain coefficient, fatigue strain coefficient. C is a Coffin-Manson exponent. Okay, so this is how mathematically people do establish, okay, how the strain amplitude changes. Okay, when you change the strain amplitude, our number of cycles are going to change. Okay, the relationship between strain amplitude number of cycles to failure is expressed, okay, by using these two equations, Baskin plus Coffin Kaufman-Monson equation to establish complete SN curve of the material. Okay, so if I want to get my transition number of cycles, what should I do? At the transition, okay, what happened here? Okay, both the strain amplitude is fixed, is constant or not? What do you say here? At a transition, okay, your strain amplitude is equal. Okay, you simply equate these two. Simply equate these two equations, these two terms, we'll get the number of cycles for the transition. Researcher people establish, okay, mathematically we'll come to know, okay, for a given material constants, the sigma f prime, epsilon f prime, b, c, these are actually material constants depending on material, and E is a elastic modulus, okay, of the material. So now once you know my material constants, okay, I can know what the, okay, number of transition, number of cycles to failure. Okay. Research people establish, okay, for the transition from low cycle to high cycle fatigue of a given material. Okay, is it clear about this train life approach, basically which involves both, okay, high cycle fatigue and low cycle fatigue? So most of the times, okay, the Kaufman-Monson only talks about a low cycle fatigue. So high cycle fatigue, okay, curve will be represented by Baskin equation. Any doubts here?
Sir, what is that B and C denotes?
B and C, these are exponents, okay? Pascal
Constant
exponent,
value?
these are constant values. These are constant values. B and C are constant values for a given material. For a particular material, B and C are constant.
So it does not depend upon strain amplitude? It will
No,
not change?
these are material dependence. Okay? Material
Okay.
dependence. Material to material, the B, C, okay, sigma f prime and epsilon f prime are going to change.
Okay, okay.
Sir, shouldn't the elastic strain be constant with respect to number of cycles? So why is it changing?
Why? No, why? No, no.
So
What we are seeing, we
why
are
is there a slope in elastic strain?
no, no. Here actually we are talking about strain amplitude. Okay, we are giving within elastic. I can give. We know that. Okay, we have 0.2% strain. Okay, assume that it's a elastic strain. Okay, we are what you are doing. We are, okay, strain amplitude is subjecting within elastic deformation. Within elastic, okay, that small amount of strain. Okay, we are deforming. So, for example, my yield stress of a material is a 400 megapascal. Okay, what I'm trying to do, my strain amplitude comes below that. Okay, that means the material is still under elastic strain only, but it's a
Okay.
range. Okay, changing a range. Okay,
Hmm.
it's amplitude. Okay, keep that means strain
Okay, okay.
amplitude. Okay,
Yes, yes. Okay, okay.
so I am deforming material between those strain limits. Okay? Still,
Hmm.
those strain limits actually in a bulk. Okay, it is a elastic strains.
Okay. Okay, sir.
Okay.
So you told Baskin is elastic and coffin is plastic?
Yes, you're
Okay,
right.
okay, okay.
That's what if you look at here, the elastic strain, the related thing. Okay, this is a B. Okay, this is a C. Okay, it's a plastic deformation part. Okay, okay. So this is about the strain life, okay, approach, which basically used to establish a full range of, okay, SN curve, okay, over a range of one cycle to, okay, as many cycles, okay, 10 power 9 cycles also can establish. Okay, you'll get a complete stress strain curve using a strain life approach. So strain life approach, most of the time initially people used only, okay, for just to understand the low cycle fatigue. For understand low high cycle fatigue, people use, okay, stress life approach. So, so if I take, okay, three different materials, one is ductile, okay, other one is just strong, okay, and tough. Okay, when I say ductile, okay, here actually low strength, okay, and little bit ductility is there. Okay, toughness basically we are talking about, okay, strong. Okay, here basically I'm talking about one in terms of a which can undergo significant amount of, okay, strain, okay, strain and strength. So if I look at typical, okay, curves, what we see, this SN curves, okay, they establish SN curves in the from a strain life approach. So the ductile, okay, curve, okay, will be like this. Okay, strong material will behave like this, and tough material will be intermediate between these. Okay, what does it mean here? Okay, So when the material is strong, okay, when the material is strong, if I apply same, okay, so for example, I'm applying a same amount of, okay, strain amplitude, okay, the strong material is going to exhibit, okay, better, okay, high cycle fatigue as compared to ductile material here. Okay, it is going to be opposite when you talk about low cycle fatigue performance. So the performance of a material is going to vary, okay, depending on high cycle fatigue or high low cycle fatigue, what you are talking about. Okay, so for the same, okay, composition, everything same, but one material, okay, the same composition, but it's one is behaving ductile, other one is becoming like a close to brittle kind of. When I say strong, means close to brittle, and other one is a tough in nature. Okay, so the material performance is going to change, okay, with even, okay, within a fatigue. So low cycle fatigue performance is going to be different than high cycle fatigue performance. Okay, so once I fix, okay, my strain amplitude or stress amplitude, okay, strong materials going to behave better under high cycle fatigue performance, whereas under low cycle fatigue performance, ductile materials are going to behave better. Okay, so this is how, okay, the material, look at here the transition. Okay, I think these materials also undergo, okay, kind of transitions about 2 in 10 power 3. This is not, this transition is different. Okay, here what I'm talking about, the material, okay, if the material composition, everything is fixed, somehow I made one is strong. Okay, like if we take a steels, okay, if you take martensite, got a martensite. In other case, I got a fully annealed material. In another case, I got a normalized material. Okay, normalized materials are going to behave better, tough. Okay, those are going to be tough. Okay, annealed material is going to be ductile in nature. Okay, martensite is going to be strong. So accordingly, we look at it, the performance is going to vary. Okay. So that's a, okay, if the material, okay, if it is strong, that elastic performance, okay, is going to be better. Okay, that means high cycle fatigue performance is going to be better. Okay, when you go to low cycle fatigue, we need to have a good ductility. Okay, so if the if ductility is good, the material is going to behave better in, okay, low cycle fatigue resin. Okay, so you have to be very cautious. Okay, one has to know the particular component, whether it undergoes, okay, low cycle fatigue conditions or high cycle fatigue conditions. Accordingly, the material selection has to be done. Okay, is it clear here? Hello.
Yes, sir.
Okay. So the material, okay, so the material performance under low cycle and high cycle fatigue, okay, conditions going to be vary. Okay, so depending on, okay, so many factors will influence. Okay, so if I want to have a better low cycle fatigue performance, the material should exhibit significant amount of ductility. Okay, so it should have good amount of plastic deformation. The material actually having, okay, only we are talking about low high cycle fatigue conditions, ductility is not so important. Okay, with small ductility is good enough, but material has to be strong enough. Okay, so I think, I'll right now, what is time? Yeah, still we have time, 5 more minutes time. So we do, okay, establish cyclic stress strain curves. Cyclic stress strain curves, like a monotonic conditions, when you deform material under tension, uniaxial conditions, we get a stress strain curve. Okay, similarly, people also establish, okay, cyclic stress strain curves. Okay, the subjecting material under cyclic loading conditions, we can establish a cyclic stress strain curve. So for a polycrystal, if you take a polycrystal, okay, one actual condition is annealed material. Okay, other one is a cold work material. Take two different types. Okay, same composition, everything same. Okay, one actually in fully annealed condition, other one is in the cold work condition. If I deform those two materials, okay, same composition, only thing, condition, working condition is different. On annealed condition, other one is work condition. If I deform under tension, okay, if you talk about monotonic condition, okay, annealed material is going to have a low strength. Okay, whereas cold work material is going to have a, okay, higher strength. Okay, if I take these two materials, okay, independently and subject them to same cyclic loading conditions, same, okay, same material, two materials subjected to cyclic loading conditions, the stress strain behavior is going to be like this for both the materials. For both the materials, the stress strain behavior is going to mono annealed conditions. Okay, if I deform annealed material under cyclic loading conditions, we do see cyclic hardening. We do see cyclic hardening. If I take a cold worked material, okay, if I deform material under cyclic loading conditions, it's going to undergo cyclic softening. Cyclic softening, okay, under cyclic loading conditions. Okay, so this curve, stress strain curve, okay, under cyclic loading conditions, okay, will be like this. Okay, that means the material which gets strain hardens under monotonic conditions, okay, which will get strain hardened. Okay, that can also lead to strain hardening. Okay, in the under cyclic loading conditions. If I already have a cold work material, already it has a lot of dislocation density. If I deform that material under cyclic loading conditions, it undergo softening. That is called cyclic softening. Okay, so this kind of curve is established, okay, from deforming a material. Okay, you fix the strain limits and change the strain limits and establish my a loop, a saturated loop, okay, at a different strain ranges, change the strain ranges and establish loops. Okay, I can get the locus of each locus point of each saturated curve. If we connect them, we'll get a cyclic stress strain curve. Okay, so this is basically in the tension part. In a compression, if we talk, okay, you'll also have a different stress strain curve in the other negative direction, okay, negative compression direction. So in one quadrant of this thing, we go, what is showing it's basically one quadrant of this thing. So this can be obtained from by subjecting the material under strain ranges, change the strain ranges and get a saturated loop, and connect the locus of each saturated loop. That gives you cyclic stress strain curve. Okay, any doubts here? Are there any doubts? Yeah. If I take single crystal, okay, so there also we subject the single crystal to fixed strain limits, and we establish these loops, okay, saturated loops, and connect the locus of each saturated loop. We'll get a stress strain curve, okay, of the one quadrant, okay, positive quadrant was taken. So we get a this kind of stress strain curve under cyclic loading conditions. Okay, so each the region is going to experience different type of microstructure evolution. So microstructure is going to evolve under cyclic loading conditions. However, that evolution is going to change depending on how much strain you have given, and the kind of features, microstructural features what we see are also going to change with amount of strain what you are giving to the material. So in a single crystals, we typically see veins structure, persistent slip bands, labyrinth kind of structures, and dislocation cells are going to develop. Okay. In case of polycrystalline materials, we don't see vein structure because directly we do see persistent slip bands and dislocation cells development. Okay. So as far as microstructure is concerned, how the microstructure is going to evolve under cyclic loading conditions. What is meaning of vein structure? We do see like this. Okay, if you go to high magnification, okay, after deformation, okay, stop the material, okay, stop the material, okay, at this thing location and see how the material is going, what kind of microstructure is going to have. We are going to have a vein structure. If I deform further, higher strain, okay, we do see formation of persistent slip bands. When you say persistent slip band, okay, what you are seeing, okay, free of dislocations. Okay, these bands look like exactly like a parallel bands. Okay, so these bands will have a very low dislocation density as compared to adjacent region. Okay, these bands will have a low dislocation density because we do see under cyclic loading conditions, we do see recovery is going to take place. That can lead to annihilation of the dislocations in certain bands. Okay, those bands are called persistent slip bands. So where labyrinth structure, basically what you are seeing, okay, we also see if you go to higher amount of strains, we do see this kind of formation of this kind of texture, okay, structure. It's called like a labyrinth kind of, okay, where you start, where you end, okay. One has to see like that kind of structure will be seen. But if you go to higher amount of strains, in the material under cyclic loading conditions. So I'll stop it here. Okay, we will discuss what factors can lead to crack initiation and how the crack is going to propagate under cyclic loading conditions. Okay. In next class, we'll discuss about crack initiation, crack propagation, and cyclic loading conditions. Any doubts here? Are there any doubts? No? Am I audible?
Yes, sir, you're audible. Sir,
Okay.
about the term paper,
Mhm.
you said you were going to give instructions. So, is that already there? Or have I missed it somewhere?
Instruction presentation, you're talking about report already given, I think. It is there already.
Are all the instructions being given on mail or on Moodle?
It is there
Anywhere?
in the and same, I think, topics, everything have been uploaded. That also has the instructions
Okay, okay.
already uploaded. Okay, instructions plus topics. Okay, instructions for writing report I had given. Okay, not for the presentation. Any doubts here?
Yes, sir. Sir, slide number 17.
Yes.
Sir, why softening occurs in cold work material after cyclic loading?
See what already it is during cyclic loading conditions we are changing the loading direction, one forward and backward we are giving. Okay, so during that deformation, reverse direction, whatever dislocations are there, those are going to get realigned. Okay, so that can lead to recovery, annihilation of dislocation are going to take place.
Yes, sir.
Okay, during, if you take a fully annealed material, during cyclic deformation we are still generating more and more dislocations.
Okay, sir.
So that lead to cyclic hardening. Okay, because the materials, usually strain hardening materials, going to lead to cyclic hardening. Cold work material already you have it deformed, fully deformed. Now what
Yes, sir.
happens is there no no additional dislocations are going to form. Basically rearrangement is going to take place. So during reverse direction, it can undergo, we can see annihilation of dislocation that can lead to softening of the material.
Okay, sir.
Any other doubts? Okay, if there are no doubts, I'll stop recording. So please let me know if anybody has doubt. They can stay back. Okay.
Thank you, sir.
Thank you.